These are the 5.3 Part 1 notes, and we're going to start looking at exponential functions, and we're going to continue this with our next set of notes as well. So, first of all, laws of exponents. This is all review. You guys started learning this in pre-algebra. You covered it again in Algebra 1. I know you touched on geometry in Algebra 2. So, you've been doing these exponent rules for a while now, and as we go on through the course, we're going to be doing refreshers on these exponent rules. But some things that we have to remember is if I have the same base, 2 to the s times, or a to the s times a to the t is equal to a to the s times t. And a quick example of this is I can do 2 to the third times 2 to the fifth, and this is going to be equal to 2 to the eighth because I add 3 and 5. Now, things that I can't do, if I have 2 to the third plus 2 to the fifth, I cannot do this. This does not become 2 to the eighth. I cannot add them to create this. So this is a no-no. You can't do that. Other things that I cannot do, I cannot say that 3 to the third times 2 to the fifth is equal to 6 to the eighth. It does not work that way. This is also something that does not work. So I cannot multiply things out and then add exponents. I can't do that. If I have different bases, I actually just have to go through and perform the math. If I have addition, I have to go through and perform the math. I can't just sit there and say, all right, different bases, let me multiply and then add. If you have the same base and you're raising it to a power, you can do that. And we're going to see this a lot more with variables. So it doesn't really matter so much when we have numbers that we can evaluate, but if I have something like x to the third times x to the fifth, well, then I can go ahead and say that this is x to the eighth. So there's an example there. If I raise a power to a power, it's raising it to another power. So this is like saying 2. If I said 2 squared, this would be equal to 2 to the fourth because I multiply those out. So this works when I have x to the fourth squared, then I can say that this is like x to the eighth. That allows me to raise a power on my variable. And you multiply those out. Make sure you don't add them. So that's something that often happens when you raise those powers. You think that you're adding them, you're multiplying them always. If I have two variables times each other raised to the same power, I can split that up into those two different bases raised to the same power. So this is where if I had like, again, this doesn't make so much sense with numbers. If I had 2 times 4 squared, this would be equal to 2 squared times 4 squared. This makes sense, 2 times 4 squared, so that's 2 times 4 is 8, 8 squared 64, 2 squared is 4, 4 squared 16, 4 times 16 is also 64, so we can quickly see mathematically how that works out. This is going to do us a lot more when we're saying things like 2x squared, where I can turn this into 2 squared times x squared or 4x squared. We've done this before, we've seen this before. Or if I can say something like xy cubed, this is the same thing as x cubed times y cubed. They still work out. So if you have different bases to the same power, then you can combine them. 1 to any power is always 1. This makes sense because let's say that I had 1 squared. Well, that's just 1 times 1, which is still 1. If I had 1 to the fifth, this is 1 times 1 times 1 times 1 times 1, which is still just equal to 1. So 1 to any power is always 1. If you raise something to a negative power, we have to remember that this flips where the variable is in terms of the denominator. So this becomes 1 over a to the s, which is equal to 1 over a to the s power. So if I said something like 3 to the negative 3, this is equal to 1 over 3 cubed. Or if I said something like z to the negative 5, this would be equal to 1 over z to the fifth. If I had something as 1 over x to the negative third, well, then I have to move that up. It works both ways. So this would be equal to x to the third. If you have 1 over x to the negative third, it's the same thing as x to the third. So if you have that happening, you switch them around. And then anything to any power is 0. 1 to the 0 power or is 1. 2 to the 0 power is 1. 3,333 to the 0 power is also 1. So those are just some properties of exponents that we need to make sure we know. You've done all these before. Now we're going to move forward with them. An exponential function is a function of the form f of x is equal to a to the x power, where a is a positive real number and a does not equal 1, because again, if a was equal to 1, if I said 1 to the x power, this would just be the same thing as saying f of x is equal to 1, because no matter what number I put into x, your value will always be 1, so that's just a linear function. So a can't be equal to 1, A has to be a positive number, and the domain of f is the set of all real numbers. So your domain here is all real numbers. Whenever you see an exponential function, you always have a domain of all real numbers. It's nice and easy that way. And your a value has to be greater than 0 as long as it's not 1. So you can have fractions raised to a power, anything, but it has to be a positive number. A has to be positive, and it cannot be 1. Now, this is what a graph of an exponential function looks like. You kind of have this like upward sloping thing, and you can even say that it looks like 1/2 of a quadratic almost. It looks a little bit different, but from the positive numbers, it resembles something similar to a quadratic. It's not quite, but again, it's kind of that quick building, goes up right away. The difference is the negative side of an exponential graph. It's really, really small. So when we think of an exponential function, we're thinking about the fact that we have f of x is equal to 2x. Our x value is the exponent, and we're changing what that exponent value is. Every single time something happens, we change that exponent. We're not changing anything. It's not like a quadratic where we're changing a number that is then raised to a power. We're actually changing the power we're raising a specific number to. So the easiest one to work with is f of x is equal to 2x. That's the smallest whole number we can have an exponential function with. So negative 10, if I plug negative 10 in as my x value and I made my table of values, 2 to the negative 10 power, we've already found that this is the same thing as 1 over 2 to the 10 power. And 1 over 2 to the 10 power is going to be equivalent to about 0.00098. 2 to the negative third power is the same thing as 1 over 2 to the third power, which is equal to 1 over 8, which is about 0.125. 2 to the negative 2 power is equal to 1 over 2 squared, which is the same thing as 1/4, which is 0.25. So what we can see here with these exponentials is with our negative numbers, the larger the magnitude of that negative number, the smaller your y value is. Because again, it's that theory that we learned back in 4.2 with our functions. If I put 1 over an extremely large number, it becomes 1 over infinity, and 1 over infinity is getting closer and closer to 0, because if I'm dividing 1 by a number much larger than 1, I'm dividing that 1 into very, 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 very small parts. So if I raise 2 to the 100th power, that's 2 times 2 times 2 times 2 times 2. That's a lot of 2's multiplied by themselves. We're talking about something in the billions of numbers. 1 divided into a billion parts are these very, 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 very small parts. So what happens is with my negative x values, my graph is getting really, really, really close to 0. Now it's never going to actually equal 0. It never gets to the point y equals 0. Because again, I can divide 1 into a billion parts. I can divide 1 into 6 billion parts. I can keep dividing 1 into these infinitely small parts. But as I keep getting them smaller and smaller and smaller, I'm never going to get to the point where I can divide 1 to the point where there's 0 parts. I cannot break up 1 so each part of 1 is 0. I can break it up to the point where it's almost like I'm talking about close to nothing, but it's still something. It's like if I were to take like one human cell, I could break that up into thousands upon thousands of atoms, and then among those atoms I could break them up into neutrons and protons and electrons, and then from there I could get the neutrinos, and I could break them down into the subatomic particles, and we could start looking at all of these little things, and they get smaller and smaller and smaller, and it's so close to being nothing, but it's not nothing. So it will never equal 0, but I have that horizontal asymptote at y equals 0 because it's going to get really, really, really close, but it's never actually going to be equal to 0 across it. Now on the positive side, your numbers start getting large right away. If you have 2 to the first power, that means you're plugging 1 in for x, that's 2. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, and it keeps going up and up and up, and they rapidly multiply. They're exponential. It's exponential growth. It gets faster and faster and faster. So really quickly with exponential functions, you'll find that your y values are very, very large, especially when we're working with any form of a number greater than, I would even say, like 3 and above. Even 3 is really, really quickly growing. So what happens is your y values are rapidly becoming very, very large. And we can see here with how this graph is scaled, we can't even get to x is 3 before it goes off this graph. And even if we grew this graph out to 10, if I made my top y value 10, I could still only get to x is equal to 3, and then once I get to x is equal to 4, it's off the scale of this graph. There's not much that's fitting within this graph. So I'm sure we've all heard the things like, you've heard the term, things are growing exponentially. And the easiest real-life application of exponential functions is actually happening to us right now. I can't tell you that last year, as COVID started picking up right as I was teaching Chapter 5, and it is a really, really good use to say, okay, we can look right at this real-world event, and then we can see how this is impacted by mathematics. And I'm sure you're looking at this and saying, Mr. Yehlen, this graph clearly has ups and downs. It's not just going up and up and up. Well, yeah, you're right. This graph isn't perfectly exponential. When we're looking at things in math, rarely do things in the real world adhere to things perfectly, but we can actually start making models. Now, this is from the New York Times. So they take a rolling 7-day average to make this line that goes across the graph. But if we start looking at peaks and only peaks, we can see periods of exponential growth. We can see exponential growth here. We can see exponential growth here. We can definitely see exponential growth starting right after October into November when we're looking especially at peaks. And we can see it again right after December. We kind of have these quick periods of large upticks. And those are all periods of exponential growth. We have multiple exponential functions that are happening here. You might even be able to argue in some cases that we have exponential functions happening the other way. We've got exponential drops. We've got periods of time where the number of new cases are going down significantly. So this is when people aren't in contact with each other, when the virus isn't able to spread. When we take away that transmission method, exponentially it goes down. So we can see how little factors can make these things go down and go up quite a bit. Now, this is not. This is also kind of public safety announcement for Prairie here. Make sure we're washing our hands, wearing our masks, keeping a distance. It allows us to reduce the spread. And this is kind of one thing that virologists, the CDC, this is where we're getting projections from, is looking at these trends and then knowing what an exponential does. Now, it's not always perfect. We've seen how those trends, how some of those numbers predicted didn't exactly come true. And again, that's because we took mitigating factors. But we can look at this and we can see, okay, here is a real world example of what an exponential function is. And you'll find that every virus adheres to the idea of what an exponential function is. All right, the next example I have of graphing an exponential function is again from the book, and this is if we were looking at 1/2 to the x power. So again, looking at this, if I've got 1/2 to the negative 10th power, this is the same thing as saying 1 to the negative 10th power over 2 to the negative 10th power. So I flip these upside down. This would be 2 to the 10th over 1 to the 10th because they flip places in the fraction. Just like 1/2 to the negative 3rd power is equal to 1 to the negative 3rd over 2 to the negative 3rd, and they would switch places in this fraction based off of our exponent rules. And this happens over and over, so then I'm actually looking at 2 to the 10th power. I'm looking at 2 to the 3rd power, so on and so forth. So 1/2 to the negative 10th power is 1024, because it's actually the same thing as 2 to the positive 10th power. 1/2 to the negative 3rd power is the same thing as 2 to the 3rd power. So it just flips the graph. This flips the graph among the y-axis. And when we look at it flipping the graph among the y-axis, we can say that 1/2 to the x power and 2 to the negative x power are the same thing. Because let's consider if I just plug this in as 2 to the negative x. Well, if I plugged it in as 2 to the negative x, then I could say down here, all right, 2 to the negative 10th is just equal, or 2 to the negative 10 is just equal to 2 to the 10th. 2 to the negative 3 is just equal to 2 to the 3rd. And then this starts giving us the idea of transformations. So if we recall from our transformations chapter, if I put a negative x, this is the same thing as reflecting or flipping about the y-axis. And I can look at this graph, and I can see that this graph here is nearly identical to this graph up here. The only change is I flipped it among the y-axis. So what this leads us to, and this is just kind of a general introduction, I'm not going to go through the full proof here, is that I can think about exponential functions as transformations. I can use the exact same transformation rules that I learned all the way back in section 2.5, and I can apply those to exponential functions as well. And you might be asking, Mr. Yehlen, how can I apply those to exponential functions? Well, here's some information that you 100% need to write down, and I would put this somewhere special in your notes. I would star it, something. When making transformations for exponential functions, we're going to have a table of values here. And there are 3 points I want you to be concerned with exponential functions. If you have an x of -1, your y value is going to be 1 over a. And this is in the general form of f of x is equal to a to the x. A to the x power, and a represents any base. If you have an x value of 0, y is always 1, because anything to the 0 power is always 1. And if your x value is 1, you have a. These are the 3 points I'm most concerned with you being able to graph. You can go on and you can make it more specific. Like I could turn this into a little bit longer. Like I could say that if you have -2, this should be 1 over a squared. -1, 1 over a. 0, 1, 1a. 2a squared. You could make it longer like that, but I really don't need you to go crazy here. Let's just think of the basics of what an exponential function is and the basics for my table of values when I start applying my transformation. So I have this f of x is equal to a to the x, so when I have my basic table of values, I've got x is equal to -1, y is 1 over a, x is equal to 0, y is equal to 1, x is equal to 1, y is equal to the a value. So I've got a transformation graphed here. This is from the book, so we already have the end result. Let's see if we can make it match the end result. So I've got graphed the function f of x is equal to 2 to the negative x minus 3. So here my parent function, not only is it f of x is equal to a to the x, well now it's very specific in f of x is equal to 2 to the x power. I've plugged in a for 2. So my original table of values here, x, y, I've got -1, 1 over 2, because 2 is my a value, 0, 1, and 1, 2, because 2 is my a value. And then I'm going to go through transformations the way I did in 2.5. First thing I'm going to do is I'm going to move from the inside out. So I'm going to look at what happens to my x first, which is -x, and I'm going to find f is equal to 2 to the negative x power. When you have 2 to the negative x power, remember that you reflect it about the y-axis. So what happens here, when I reflect about my y-axis, +1 becomes my -1 value, so this is 2. 0, 1 is going to stay the same, and then 1 would become 1/2. So these kind of flip around. This y value gets moved here, this y value gets moved there, and then 0 always stays the same. When you flip about your y-axis, when you reflect over your y-axis, your y value at 0 stays the same for 0. So now that I've done that, I'm going to do my next transformation, which is f of x is equal to 2 to the negative x minus 3. And here, this is a y value shift, so this is a shift down 3. And it's a shift down 3 because it's happening outside the y. How do I know that it's happening outside the y? If it was happening to the x, it would still be in the parentheses. So if I had something like 2 to the negative x plus 5 minus 7, well, then this would be my y value, and then this would be my x shift, or horizontal shift. This is my y shift, or vertical shift, where it's happening outside. So if you have something happening in the exponents, that's a horizontal or x value shift. Anything that's not happening in the exponent is going to be a y value or vertical shift. So what this means is that I take all those y values that I found in my previous one and I subtract 3 from it. So I've got xy, I've got -1. 2 minus 3 is -1. I've got 0. 1 minus 3 is -2. I've got 1, 1/2. 1/2 minus 3 is -2.5. Now let's go ahead and look at our graph here. I've got 1, -5/2, which is the same thing as -2.5, 0, -2, -1, -1, and then it would keep on going from there. And we have our general shape for the graph. Once you had these 3 points, you could just go ahead, graph through it, go up, and then go in the reverse direction. What we have to remember is that I had a horizontal asymptote. For the parent function, your horizontal asymptote was y is equal to 0. When you do a vertical shift, your horizontal asymptote is going to move with that. So because you started at y is equal to 0 and your horizontal shift was -3, that new horizontal asymptote is going to be y is equal to -3. Your horizontal asymptote just moves with your vertical shift. Does not change with your vertical stretch, does not change with your horizontal stretch, does not change when you reflect around the y-axis. Your horizontal asymptote is based solely on your vertical shift and how your vertical shift relates to that original horizontal asymptote at y equals 0. So that's how you go about graphing exponential functions. And we can get more into this in class. I encourage you, when you're working on these homework questions, make sure you're coming up to me and asking me questions. I realize that this can get kind of confusing, especially when we're just applying it as transformations and only looking at 3 points. But I promise you, if you start practicing those 3 points and doing those same transformation rules, this is a lot easier than just plugging numbers in and trying to get a shape of your graph. All right, so now we're going to look at the number e. And we're going to get kind of like, this is really, really, really big level stuff to think about how the number e was created. So Euler, the famous mathematician, a man who is much smarter than most people will ever be, was able to look at nature and determine that this number e happened a lot. And he was trying to figure out, how do I define e? He found out that a lot of things in nature behaved according to exponential growth, and it didn't behave according to exponential growth in terms of one number. It behaved, or in a whole number, it behaved in kind of a weird number. And he tried to figure out, how do I define e? Well, he figured out what e is. We're going to have to start thinking about calculus, because you guys don't know what limits are. So this is kind of explained by calculus, which you haven't learned yet, but you will learn next year. E is defined as 1 plus 1 over n to the nth power. And it's not only 1 plus 1 over n to the nth power, it's 1 plus 1 over n to the nth power as n approaches infinity, so as n becomes a bigger and bigger number. What does this mean? Well, let's start thinking about n as n approaches infinity. The idea of n approaches infinity means, what does this equation look like? What is the approximate value if I plug a very, very, very big number in for n? And the book gives us a table of values, and we can see from our table of values that the larger and larger that we plug in our numbers, if I plug in just 1 plus 1 over 1 to the first power is 2, because it's 1 plus 1, which is 2, and that's 2 to the first power. So you might expect, okay, this is going to become a very, very big number. Well, what we see is that it actually doesn't get too much bigger than 2, because when we take 1 and add it to 1 over 2, that's 1.5. 1.5 squared isn't too much bigger than 2. It's still a relatively small number. 1 plus 1 over 3 is 1 plus 1/3. So that's 1.33 to the third power. So what we see here is we're actually making smaller additions to 1. 1 plus 1 over 4 is 1.25 to the fourth power. So yes, we're multiplying this number out more often, but we're actually making that number we're raising to a power smaller and smaller and smaller. And it just keeps getting smaller and smaller and smaller. 1 plus 1 over 10 is 1.1. 1.1 to the 10th power doesn't really get that big. And what we see is, no matter what number n we plug in, once we start getting above, once we hit 10,000, once we get above 10,000, we always see that the first 3 decimal places are always 2.718 at 10,000 and above. We can see that at 100,000 and above, it stays 2.7182. At 1,000,000 and above, we can see that it says 2.71828. So we can get further and further. The larger and larger the number we plug in, the more and more we can be sure of the decimal places that happen after. And this is what e is defined as. It's said to be a number as n approaches infinity. So as n gets bigger and bigger and bigger, we can see really quickly, once we're at 1,000, it's not really getting above 2.7 that often. So what we do is we approximate e to be 2.72. So the number e, and e is a number, is 2.72 approximately. E is just like pi. It's a symbol that represents a number specifically. So e is not a variable. E is not something that we can be plugged in for. E represents a very specific number, 2.72. And you might ask, Mr. Yehlen, why would we not just put 2.72? Well, at the end of the day, it's just like with pi. We don't plug 3.14 in for pi into an equation because pi is this irrational decimal that goes on forever. E is the same thing. It's an irrational decimal that goes on forever. If we can plug it into our calculator, we're going to get a much more exact answer than if we just divide by 2.72. And we're often going to be using e in terms of having a calculator because we want those more exact answers. So the graph of e to the x looks a lot like a graph of any other exponential function. You've got a y-intercept at 1 because whenever you have something to the 0 power, your y value is 1. And all of these, this is just 1 over 2.72 squared. 1 over 2.72. This is 2.72 squared, so on and so forth. It's a little bit more exact when we plug in e to our calculator, but this is the general graph of e, and these will be the points you use when you transform the graph of e. So if I want to graph e to the x with transformations, so I've got f of x is equal to negative e to the x minus 3. So here, first thing that I can see, our book does a really good job of going through and not only giving us the transformations table by table, but graph by graph. So if I think about this, this is the graph of my parent function here. Y is equal to e to the x power. This is the graph of the parent function. Then what it's saying is, all right, e, first thing that's happening is we're multiplying it by a negative 1 on the outside. And since it's outside and not with the x, that means a reflection about the x-axis. So what this means is that I take my table of values, and I had that original table of values that I'm just going to work with 3 points. I'm going to say negative 1, 0.37, 0, 1, and then 1, 2.72. I'm making all my y values negative because I'm multiplying by a negative 1 at the end. So I made all those y values negative. I just reflected about the x-axis in that way. Next thing I have is a shift to the right because, as I said earlier, this is happening up in the exponent. And since it's happening up in the exponent, that means it is a horizontal shift. And then the horizontal shift rules are still the same if you have a subtraction. This is a shift to the right. So what this means is that I'm going to keep those y values the same as I originally had them. Or not as I originally had them, but as I've had them from that last transformation. So those y values are still going to remain. I'm going to change the color so that way we're sure that we are going through another transformation here. And then I'm going to add 3 to all of my x values because I have a shift to the right 3. And we can look here and we can see that, okay, the points that I have, 2, negative 0.37, 3, negative 1, 4, negative 2.72 all exist there. I realize I've kind of quickly gone over how to graph these, but that's because those transformation rules from 2.5 are something that we should be pretty solid in. You can always go back to 2.5 and look at those notes. I would highly advise you go back to 2.5, look at the notes from 2.5 and see all those transformation rules. Rewrite them at the top of these notes so that way we're aware of what's going on. Make sure we know what a shift is. Make sure we know what our shifts right and left are. Our general form for this is going to be f of x is equal to, this is a little bit different. So I'm going to say, yeah, let's do this. A times e to the bx minus h plus k. And all of these are the same. A is still your vertical. A is your vertical stretch. B is your horizontal stretch. H is your horizontal shift. And remember that with your horizontal shift, a negative goes to the right, a positive goes to the left, and then K is your vertical. And we remember that a negative goes down and a positive goes up. And then again, the table of values that we want to use are for our general features. If I just have f of x is equal to any generic a to the x power, your x value of -1 will result in a y value of 1 over a, and this is for your parent function. 0 is 1, and 1 is a. And this is for any parent function, any a value you can plug in. And then we have something a little bit more specific for e to the x. And again, it still holds the same idea as a to the x, but we know what e is. So if you have an x of -1, you have a y of 0.37. If you have an x value of 0, y is still 1. And if you have an x value of 1, your y value is 2.72. And we can use those 3 points to graph our transformations, abiding by the exact same transformation rules we've been learning since 2.5. If you guys have any questions or concerns, please let me know. Reach out with any questions in the homework, and have a great night.